then I'll never understand why, because I always leave the settings the same and I always have to, who knows? Okay, so like I just said a few moments ago, the control unit is broken into two modules. A control unit FSM, and a state machine control unit decoder. Notice again, we talked about this just a moment ago, but again, just make sure everybody heard. Going into both of these modules are the opcode and the function prefix. Now, this control unit decoder also has the 30th bit of the instruction going into it. And next class, we'll talk about why that's so. Okay. The output of our FSM will look. It's mainly enables and writes. See PC write, read write, memory write enable, two memory read enables. It's got a reset. And then in red, I put these outputs in red because they have to do with what are called interrupts. And as I mentioned previously, we just don't have time for interrupts. Okay? Interrupts involve a whole other piece of hardware, a few more instructions. To do it any justice, I would have to give you another activity, and it would make the final project more to do. And I just feel like there's not enough time. So unfortunately, especially if you're a CPE major, I wish that wasn't the case, because you'll have a class. In fact, I think the follow-on class to this, you'll definitely need interrupts, but they usually start with a good review at the beginning of that class anyway, according to Dr. Humble teaches a lot. So anyway, it's unfortunate, but we just can't do this. So the outputs of the FSM are primarily your enables for writing and reading. And then if you look at the output of the control unit decoder, well, what are these outputs here? Where are these going? ALU fun, ALU source A, ALU source B, PC source, RF, write, select. Where are those all going? The muxes. Okay, so you see the output of your decoder is controlling what the muxes are doing, right? And the muxes control how the data flows through the auditor, right? Because, for example, ALU source A, ALU source B, those are the muxes at the front of the ALU that's determining what's going to the input of the ALU. And then the ALU is going to do some either math or logic operation on that data that gets passed through. Okay. All right. So FSM, the control unit FSM, and from your CP 133, you may remember that FSMs, they're synchronous, right? Sequential. Right, they always have a clock input. As I just mentioned a moment ago, most of the outputs are enables for reading and writing. Okay, so the output of FSM, it determines when data is going to be read, when data is going to be written. Okay, and because it's controlling these read writes, it's time critical. And the read writes have to happen at certain times. Right? Like you don't write data result until you've actually done the process, right? And you don't read data until you're ready to take that data and do something with it. Okay, so that's like the basics of the control unit FSM. Now the control unit decoder, again from CP 133, you probably remember, right? It's async because you don't have a clock. Combinational circuitry. Just as we said a moment ago, the outputs are mux, selects, and the control unit decoder, it's routing the data right through the select lines of the muxes. That determines the path that the data is going to take, right? It determines the red line in our diagram, which routing data. Now, the control unit decoder, it's not time critical as long as it's fast enough. Okay, so the natural question is, well, what do you mean by fast enough? Well, I've sort of mentioned this in previous classes, and we'll talk more about it. But for most instructions, it takes 2 clock cycles to process that instruction. Okay, 1 clock cycle is to get the instruction. Okay, 1 clock cycle is to get the instruction at the output of the memory module. Okay, and we'll talk about how that's done again, although we talked about it before. Okay, so that's 1 clock cycle. The second clock cycle is getting the data from the output of the memory module where the instruction is, all the way through the reg file, all the way through the ALU and media generator, if that's needed. Again, what's exactly needed, what hardware is exactly needed depends on the instruction. But it's got to go from where the instruction is at the output of the memory module, EL1 of the memory module, all the way through, the circuitry, to the right of on your diagram of the adder, back to advancing the program counter to the address of the next instruction to be executed. All that has to be done within 1 clock cycle. So if all that's done within 1 clock cycle, then it's fast enough. Okay, so that's what fast enough means. Okay, and if you remember, I mentioned this when you were working on the ALU, because we said, because of this, right, it's going to go through all that circuitry in 1 clock cycle, that the MUX has to be something simple, right? And that's why we said, just use 1 case statement for the MUX, because the Vivado, when it synthesizes the hardware for that, it should just be a single MUX if you use a single case statement. Okay, as opposed to if you use an if statement or if statements, you're going to get a chain of circuitry that's going to, increase the time it takes to get through all that. And that's likely, to cause your adder to have issues when you have it all connected together. Okay. All right. So, any questions up to this point before we talk about the state diagram for your control unit FSM? Because that's where you always start with a finite state machine, right? In CP133, you learned that, right? You always start with a state diagram anytime you're doing an FSM design. Okay, so everybody's good? All right, well, here is the state diagram for our control unit FSM. And it's only 3 states. Now, if you were in my CP133 class, you did more complicated state diagrams than this, right? Because we had state diagrams that had, at least a half a dozen or so states. Okay, so the state diagram is not all that much, but you'll see that within the execute state, we need quite a bit when it comes to the coding part. We'll get to that. Okay, so there's this state here. Okay, init is short for initial. Okay, so this is the initial state. Then we have a state called fetch. You'll see where the name comes from coming up. And then we have a state exec, which is short for execute. Now notice that we've got this arrow coming into our initial state. That's to symbolize an external reset. RST, external reset. So if you look at the adder diagram that every table could have, see the RST is right there. Okay, it goes directly into the FSM. That's an external reset because that will connect to a button on your basis board. Okay. So that's an external reset. We also have another reset that's an output of the FSM. So right here, these are not the same. Okay, these are different resets. This is an external one, as I just mentioned. This one here, this output goes to the reset that's on the program counter. If you look at the program counter in the lower left, see that RES EP, that's this. Okay, see, this reset going to the program counter is coming from the FSM. This external reset is coming from a button on the board. They're completely different. In fact, it might be better to label this PC reset. Like when you actually design this, instead of just calling it reset, it might be better just to label it as PC reset, so you know it's to reset the program counter. Okay, so in the initial state, we want to reset the program counter. So we want that PC reset to be active, and we made that reset an active high, so we would make it a 1. So in the initial state, once this is active, right, active high made a 1. Well, on the next clock edge, since it's synchronous, on the next clock edge, the output of our program counter is going to go to 0. Okay, and what does the output of the program counter provide? The address of the instruction that's going to be executed. And why do we want to start at address 0? Right, because that's where our program starts. Your first instruction of your program is always at instruction 0. That's always the case. Okay, so that's why we initialize the program counter to 0, because that's where the first instruction in our program is. Okay. All right. So, we have it equal to 1. The next clock edge happens, right? Puts us at an address where the first instruction of the program is. And now we go into the fetch state. And it's called a fetch state because this is where we get the instruction. Okay, we're fetching the instruction. Right, the instruction that the program counter is addressing. And in order to get that instruction to be at the output of our memory module, right, DOut1, you remember there's a input to the memory module that we need to activate, that we need to make equal to 1. Okay. All right, this enable right here, then read enable 1. Okay, so you see in this state, then read enable 1 has to be made a 1 because we made it active, or actually Dr. Hummel made it an active high because he did the memory module. Okay. So when this is active on the next clock edge, because it's synchronous, right, at the time of the next clock edge, the instruction that's being addressed by the program counter is going to be at the output of the memory module. Okay, and then it goes into the execute state. And this is where you make the instruction happen. And how do you make it happen? By controlling how the data goes through the Otter hardware. So you see, this is where you have to know what the data path and the control signals are from each instruction. Because in the execute state, that's where we're going to make it happen by these outputs, right? These controlling the muxes, these controlling when reads and writes happen. And then once you're done executing an instruction, well, you go back to fetch to get the next instruction. Okay, so you see that's our state diagram. It's just 3 states. You go initial to fetch, fetch to execute, execute back to fetch, fetch to execute. You just stay here until your program has been all executed. Okay, so we answered this question here, right? Why is the program counter reset to 0 initially? Why is that again? Because that's where it says, yeah, that's where the first instruction is. Address 0, where the program starts. Address 0. Okay, and I mentioned this, right? In the fetch state, we enable the read, and then at the time of the next rising edge of the clock, that's when the instruction to be executed is going to be at DOut1. Okay, then when we're in the execute state, well, now we have to make our read and write enables and our mux select such that the instruction that has to be executed is going the right path.
When we say PC is reset to 0, I don't know if I missed this, but yeah, are we saying that the actual PC counter are the program counter, the actual one is equal to 0, or are we saying that there's a variable inside of the FSM that's set to 0?
No, we're saying that, let's see, we're gonna make the code such that when this is a 1 and we get a rising edge of the clock, it's gonna be synchronous, it's gonna send out a reset signal to the program counter, and this has already been designed when you get a 1 on this reset to make the output 0.
Okay, so that PC is not part of the FSM. We're just noting that that's what happens
Right.
to initialize. Okay.
Right, yeah, the PC, yeah, you've already designed that. That's over here, but now these control units are controlling. Yeah. Okay, does that answer your question?
Yeah.
Okay. Okay, and then again, in the execute state, that's when the data, is flowing from, the reg file through what it needs to flow through for a particular instruction, and also it has to advance the PC to the next instruction. And again, it's got to do that all in one clock cycle. So let's see, what was the 2 things I wanted to write here? I think we already talked about them. What was it? Oh, just that again, you need to make it happen in one clock cycle. And again, this is the reason why, or because we have to make it happen in one clock cycle, this again is the reason for an efficient ALU. Again, single mux. Hopefully, when you designed your ALU, hopefully you took a look at the elaborated design to see, what the software synthesized, and hopefully it's just a single mux. If you've got something that's like a long chain of circuitry, then I doubt you used the case statement, or if you did use a case statement, maybe you got latches in there because maybe you don't have all the options covered or something. But take a look at that, because again, if you don't have just a single mux, it's going to raise issues when you connect everything up. And then also, what was the other thing now? Oh, also about that you'll need, reason. You need data path and control signals for each instruction, each real instruction. The other day, I guess it was yesterday, I did end up counting the real instructions. I never sat down and actually counted them. I just said, oh, it looks like there's 30 or so. There's actually, I think, 37. So it's actually a little closer to 40, but 30 is a nice round number. But you see, the nice thing though, even though there's 30 some odd instructions, close to 40, and you need a diagram for each one, well, you don't necessarily need 37 diagrams, because you'll have a group of them that the red lines are all the same, and just like one blue signal is different, the ALU fine. So you'll have like groups that essentially have the same diagram, except 1 or 2 things is different. Okay, so it's not like 37 diagrams, but it's still a fair amount of diagrams. Okay, now again, for hardware of 6, you only need to run the sampler program that has 6 instructions. Okay, so you don't need, all the diagrams, for hardware 6. But for the final project, that's when you got to have it, your auditor by that time, has to be able to run all the real instructions. Okay, and it's better to start early than wait until, the finals due, then do the diagrams, because you're not going to have enough time if you wait right to the end. Okay, so any questions up to this point? Okay, this was all like the preliminary to get to here where I'm gonna outline how you would model both the FSM module and the decoder module and the top module, because also in hardware 6, besides those two modules, you have to do the top module for your auditor. So you'll finally be at the point where you can connect this all up. Okay, so essentially there's 3 modules that you have to do for hardware 6. And that's why we're giving you 2 weeks, because it's not due until like March 3rd, something like that. Okay, so everybody ready for this? And actually, let me get my notes here, because without my notes, I tend to make a lot of syntax errors. We're gonna start with outlining. I'm not gonna write all the code. I'll just kind of outline it to give you an idea how you have to structure it. But we're gonna start with the FSM. Okay, so, you know, maybe you call your module CU for control unit, FSM. Like any module, you got to declare your inputs and outputs, right? So you got a fair amount of inputs and outputs here. Okay, so after you declare your inputs and outputs, the next thing to do is define states. And depending on who your instructor was for CP 133, you might have seen this before, you might not have. Now, people that took my 133 in the fall saw this. If you took CP 133 with me prior to this past fall, then you didn't see this, because I just started doing this past fall. Okay, and what I started doing was using this definition, this type definition called enumerate. Okay, ENUM is short for enumerate, and it's a way to define the states in Vivado, where instead of using binary numbers, you're using actual words. Okay, so you might have learned in your CP 133 to define like each state as a number, like, you know, state 00, state 01, state 10, state 11. Okay, which is all fine. I see some people shaking their head yes. You know, that's all fine, it will work. But the advantage of doing it this way, of actually assigning like a phrase or a word, is that one, it makes it more readable, right? Because I can look at this and say, oh, it's in the initial state. Oh, it's in the fetch state, as opposed to, oh, binary 1, 1. What state is that? The other advantage is doing it this way is that if you go in and make edits, you know, add states or kick states out, well, you don't have to worry about going back and renumbering the binary numbers for each of the states. The software will do it for you. Okay, so there's a number of good things that come out of using this type of enumeration, if you will, for the states. So I advise everybody to do it this way. And then after the states are defined, we also, you know, these states here that we have in the brackets, we also define next state and present state. And remember, you need that and you have this on here. Okay, then the next thing that comes is code for the state register. Remember, an FSM has a sequential portion to it, right? A memory portion to it, and it also has a combinational portion to it, right? That's like your next state decoder, right? To determine, you know, what is going to be the next state. Okay. So what's going to come first here? Since this is a register that has memory, what kind of block do I want for this? Always FF, right? Always FF, right? So it's going to be always FF. And you're going to make it positive edge, just like all the other sequential modules that we have. Right? So positive edge. Also, if I make a syntax error, let me know. I try not to, but I'm a little bit better when I look at my notes, but it's not foolproof. Okay, so always FF, it's a rising edge, so positive edge block, then you need your begin, you'll also have an end down here somewhere. Okay, and this is where we take care of this external reset. This external reset, it's an active high. Okay, so we'll just have an if statement. So if, and I called it CU underscore RST. Remember, be descriptive with your names. Like, I think it's a good practice to have an abbreviation for the module before any input or output. It just makes it easier when you go to troubleshoot this and you're looking at a timing diagram that has like 20 signals on it. If you just have like reset or out or in, you know, for all your modules, you're not gonna know what you're looking at, you know, so it's good to be descriptive with these names. Okay, but you would just say when that's equal to 1, that's when you want the reset to happen. So present state would be assigned the state initial, right? Because we want to go into the initial state if it's getting externally reset. So what kind of symbol do I use here, since we're in a always FF block when I go to assign? Yeah, the one with the arrow, yeah. So an arrow, and this would be like state init. We need a semicolon. Okay, so if the reset's activated, the external reset's activated, it's going to put us into the initial state. Else, what do we want to happen if we're not getting reset? We want present state to be just the next state, which is going to be determined by the state decoder. Yeah, so this would be, you know, present state assigned to the next state. Okay, and this state register, this code that you see here, just this one if statement, that's not going to change like when you do your final project. That's all you need in your state register is this. Okay, what's going to change between hardware 6 and the final project is what's in the state decoder of the FSM, as well as what's in your control unit decoder. Okay. All right, so state decoder, what kind of circuitry is this? Since it's a decoder, it doesn't have memory, so combination, exactly. So what kind of block are we going to have? Always home, exactly. So this is always home. And then we get the begin. Okay, so the next thing I'm going to put is highly recommended, but you could do it a different way. Okay. See, what I would do next is I would set all the outputs to 0. Okay, initialize all the outputs of the decoder to 0. So here we would just set. So, or excuse me, not the decoder, we're only doing the FSM, I'm sorry. Setting all the outputs of the FSM. So, you know, each one of these, you know, PC write, you know, I have control unit underscore PC write equal to 0. You know, you would just do that for all those outputs. Okay, the reason, or there's basically 2 options. If you initiate all the outputs to 0 to begin with, now when you get to your case statement, which is going to be next, well, all you have to put in the case statement is whatever output is changing to a 1. If you don't initialize all your outputs to 0 here, well, then in your case statement, you would have to put all the outputs, you know, for each part of your case statement. You know, not only the one changing to a 1, but you'd have to also put the other outputs that are 0. Okay, but if you do this first, as long as you don't change it in your case statement, it's just going to stay 0. Okay, so it's a little, I think it's a little neater and, you know, less code if we do it that way.
When we're modeling this, should we leave like the interrupt outputs and just leave it at 0? Should we just not do it?
I would not even put them. Yeah, I mean, if you did put them, like if you did put this input, you could just set it to 0, but you can just leave it out because, you know, if there was some question about whether we could fit it in timelines, you know, I might say, well, put it there if you have enough time, but we're not gonna have it. Yeah, it's just no way, because if we hadn't have lost the class to the storm, I think we could have, although it still would have been, you know, quite a bit, because, you know, we lost the class due to the holiday too. You know, like I mentioned at the beginning of this quarter, you know, and I think you've seen this, right? This class is a lot of work. There's no way to get around it. And even with a full 20 classes, you know, it's a lot, so we only had 18, and I think you're doing more than enough for 18. Okay, so after you set the outputs to 0, you're gonna have a case statement. Right, because the case statement's gonna determine where you go next, right? So what do we want our case statement to be sensitive to? When what changes? Not the clock. The state. Not the next state, but the present state. Yeah, but see when this gets assigned here, right? When present state gets assigned to next state, that's when it goes and evaluates the case. Okay, so let's see. So let's see. Am I missing any? Yeah. So it's case PS. Then you'll have your initial state. So you'll have like state, init, then begin. And again, you'll have an end. So what are we going to put here in between the begin and the end for the initial state? Because what do we want to happen here? PC reset to 1. Yeah, so you want to set PC reset to 1. And then you just want what to happen? Because where do you want to go after the initial state? Fetch state. So you're just going to have a line that sets PC reset to 1, and then you're just going to have next state equal. Actually, let's write it. See here, you're going to have CU reset. Or actually, did I call it? Well, it doesn't really matter. Or what did I call it over here? I called it PC reset. So yeah, PC reset. So just to be consistent here, PC reset. I use underscore. Yeah, underscore set equal to 1. Tick mark B1, and then you just have that next state is assigned to. Or actually, we don't put that, right? Because we're in a combinational block, so it's an equal sign, sorry. But what do we put here? The fetch state. Right, so we're just setting the signal equal to what we want, and then we're just telling it where to go next from this state. Right? So then you have your fetch state. Right, it's going to have its begin and its end. Okay, and what's going to go here? Is what do we want to happen in the fetch state? Right, you want mem read enable to be 1, and then where do we want to go after the fetch state? The execute. So you'll just have next state equals state execute. Okay, then we go with the execution states. So we have state EX EC, and we have a begin. Now this is where you would need a case statement, right? Because in the execute state, right, this is where we make the instruction happen. And we do that by controlling what the mux selects are equal to, right? That's done in the decoder. And here in the FSM, we're controlling what the read writes are for each instruction. Okay, so this is where you need the diagrams, right? Because you need to see, well, what do these read enables have to be and write enables have to be for each of the instructions. So in your case statement, what are you going to make this case statement sensitive to? Because what the opcode bits. The opcode bits, right? Because that will tell us what type of instruction And then from our data path and our control signal diagram, we can get what those control signals have to be. So yeah, this is gonna be opcode. So, let's say, we got this opcode here. And I don't know if this corresponds to any of those instructions. This may be something different, but it's the same idea. You would just have to put whatever opcode for the instruction that you need. So, right, you put this, and now you would list, CU PC write, what that has to equal. CU reg write. What that has to equal. Okay, and then if it's a different instruction, right, you're gonna have a different option here, with that opcode. Okay? And now you'll need a default, right? Every case statement needs a default. And what do you think a good default would be for this state diagram? Like, what state would you think we default to? Initial, yeah. I think that's a good default, right? If something went wacky, right, just go back to your initial state. Now, for this sample program, you're not going to need this, but just to give you a heads up, for the final project, when you have to have your auditor be able to run all the instructions, or actually, I take that back. I think you will have to do looking at my thing here. See how many we've got 2 R-type instructions, right? Oh, but it's all the same. Actually, what I'm thinking about comes up in the next module. For this module here, for your decoder part of your FSM, just a single case statement is going to be fine. But you'll see when we get to the decoder module that you're going to need like a nested, you'll need a case statement nested within another case statement. Okay, so I was just thinking ahead. For the decoder part of the FSM, this should be fine, just a single case statement where you're just putting the opcode for each of the type of instructions, and then you just got to put what, these read-write signals have to equal for that instruction. Okay, so is everybody good now? Again, I just kind of outlined this. I gave you the specifics here, I gave you some specifics here, but you got to fill in the rest of this. Right, but does it make sense as far as the flow of it? Okay, good. That's a good sign that CP 133, you retain some of that, huh? That's always a good thing. Okay, so let's move on now to the control unit decoder. So what kind of block are we going to use for the decoder? Always cone. Right, always cone, right? Well, of course, you got your module name. You'll need to declare your inputs and outputs just like always. But then, yeah, right here, always underscore cone. And then just like we did with the decoder part of the FSM, I would initialize all your outputs to 0. So now you're going to initialize all these 5 outputs to 0. Okay. Okay, now we get to the part of assigning those outputs, the mux selects, based on the opcode. So this is where you'll have your case statement. Okay, so just like this case statement of the decoder part of the FSM relies on the opcode, same thing here. Okay, so you'll have your options, for each of the type of instructions. So again, as an example, you could have something like this. In and you would put in between, what the outputs have to equal for that type of instruction. But let's say that, you have like an R-type instruction where now these two have the same opcode. So how would we distinguish between those two R-type instructions if they have the same opcode? Right, the 3 bits. So this is where you would have like a nested case. Right, so if you had, a type of instruction that, like for example, actually the LUI instruction, which is the U type, there's only 2 U type instructions, and each U type instruction has its own opcode. So this would be fine for the U type, okay? But say, again, well, actually, we can do it over here. What's the opcode for an R type that we did earlier? 33 hex, right? So we could put 33 hex here. So let's see, that'd be 0011 and 011, right? 33 hex. We need semicolons here. Again, sorry about the syntax. We're always bad at syntax. But what we would do is, when we get here, we just have another case. So you could go, let's see, it would be, I think I have the in place. I think this would just be, like case, and then you would have your function 3 code there, and then you'd have your options. And so that's putting a case within a case. You can also put an if statement within a case. And you might find that handy when you do the branch instructions for the final project. But this hardware 6, you only have 1 branch instruction, right? So you're not going to need any, extra in your, top level case. But for your final project, you're going to have 6 different branch instructions. And, for each one of those branch instructions, you'll probably need an if statement to determine, when the branch happens and when the branch doesn't happen. Okay, so for hardware 6, what we've talked about here is sufficient. But next week, before you start your final project, which will be after next week, we'll come back to this, because with additional instructions, there are going to be more nuances between the instructions. In fact, the decoder, in addition to the opcode and the function 3 bits, it has this bit 30. And this bit 30 is here because you'll see that there's a pair of instructions. Actually, I think there's several pair that have the same opcode and they have the same function 3 bits. So when you have instructions that's got the same opcode and the same function 3 bits, it's that 30th bit that determines which one it is. Okay. So, oh, and last thing here, unless you have questions, is this is how I would recommend you organizing your top module. So this is the module that's going to connect all the lower level modules together. Right? This is the module that's going to connect this diagram together. So what I would recommend, well, like always, have your name, declare your inputs and outputs. But then the next thing is define your internal signals, right? You have to define an internal signal for all these connections. Okay, and there's quite a few. Okay, and I would recommend, that you organize these internal signals when you declare them, define them, that you do it in blocks. Like, maybe have your internal signals that connect the program counter to the memory. Then have a block that connects, memory to reg file and so on. Like, try to do it in an organized fashion, because if you don't, it's easy to miss connections. Okay. Now, you already did the mux for the program counter, right? Because that was part of, what was it, hardware assignment number 2 or one of those. So you already did this mux, but there's 3 other muxes. There's 2 muxes at the input of the ALU, and there's a mux for the word data or the write data for for the reg file. I would recommend just using case statements and putting those case statements for the muxes in your top module. Right, so after you define your internal signals, you could have your case statements for your muxes. Now, another option is, you could just replicate this mux and just have like, essentially use the same file again, or you could make a different file for the mux and have it as a file. But I think it's easier just to put them in the top module. But again, there's different approaches. And then after that, now you connect your signal. Okay, you have all the code that's doing the connection between the lower level modules and your higher level. This up here in the upper left-hand corner of the diagram, that's the high-level black box diagram of the Otter. Okay, so you see your Otter CPU, it just has a few inputs. Again, we're not going to do the interrupt, so you can leave that out. You have reset, IO bus in along with the clock, and you just got 3 outputs. So you see, this gives you what your inputs are to the Otter module. It's just going to be, 3 inputs and 3 outputs. Okay, but you'll have to connect that all up to the lower level modules and connect the lower level modules all together. Okay, so you can probably see why you have 2 weeks for this, right? Because, it's quite a bit. I've given you some of it, but you got to fill in the rest of all this. Okay, so it's a fair amount. Then you have to sim it. Hardware 6, you do not download to the board. Okay, hardware 6 is getting the Otter to run that sample program made of these 3 instructions. And you just got to make sure that it's running that program correctly on the simulator. Now, let's see. Next meeting, if you look on Canvas, next meeting, there's a video that Dr. Hummel made. And in that video, he shows you what the simulation for hardware 6 should look like. Okay. Also, next week, I'm going to have an activity where I have you manually do a timing diagram for a program. I'm going to do an example in class, and then I'm going to have you do one in class on your own. Okay, so that would be some more practice on what the timing diagram should look like when a program is being run. Okay, but I would highly recommend that when you get to the point where you're ready to do a simulation of hardware 6, that you watch Dr. Hummel's video. It's about an hour-long video, but he doesn't start talking about the sim until about halfway through. And I listed it on Canvas. I said, watch it from this point on. I think it's like from the 26th minute on. Oh, okay, somebody's already looked at it. Good. Okay. Now, again, it's kind of like good news, bad news. I guess the bad news is there's quite a bit to do for hardware 6. There's no way around it, okay? But the good news is that if your hardware 6 is working, you don't have to do anything more for the top module for the final project. Okay, this top module, if it's good for hardware 6, it's good for the final project. The final project is going to entail more code in the state decoder for the FSM and more code in the control unit decoder. Okay, because you're going to add instructions. And when you add instructions, this is what gets bigger and this is what gets bigger. This is going to stay the same. The state register for the FSM, it's going to be the same for hardware 6 in your final project. Okay, so the big difference between hardware 6 in your project, code-wise, is the state decoder for the FSM and also the control unit decoder. That's where the additional code is going to go, because you're going to have additional instructions. And then the other part of the final project, which is going to take some work, is debugging, because there's no way around it. Even if your hardware 6 works, when you add stuff and because there's 30 some odd instructions, you're bound to have some instructions that don't work. And you're just, that's a big part of the final project is getting the bugs out so you have something that runs all the instructions. And that's why when you get to the final project, that's why I'll allow groups up to 4 people. For hardware 6, it's still 2 people per group, just like it's been. It's not till the final project where for the hardware part of the final project, I'll allow up to 4 people in a in one group. Yeah, I mean, if somebody wants to do it by themselves, that's fine, it's not recommended, but it's fine. If you want to stay with 2 people, that's also fine. If you want 3 people, that's fine. 4 people's fine. 5 people, not fine. Okay, it can't be more than 4 people. And that's just for the hardware part. The software part of the final project, that's still 2-person groups. Okay? All right, so do you have any questions before you get started? Now, your priority today should be to finish the branch address generator and branch condition generator, because that's due tomorrow. So if you don't have that done, that should be your priority. Software 5 is due Tuesday of next week, because again, Monday's a holiday. Hardware 6, it's not due until March 3rd, so 2 weeks from tomorrow. So you got time, but again, don't wait right before it's due. You know, you got time because it takes time to do it. Okay? So any questions before you get going? Everybody's okay? All right. And Blake's here. Blake's in the back. Hi, Blake.